we're going to continue. I think you probably could have done number 30 without me going over it, but I'm going to go over it anyway. So I have got, let me see if I can write small enough, let me start that again. Got 3 over 1 plus the square root of 6. Okay, I need to, as the instructions say, rationalize the denominator. Make a rational number up there. What do I multiply by when I have a denominator that has 2 terms in it? The conjugate, which is the difference in this case, 1 minus the square root of 6. The numerator's multiplication is going to be just the distributive property. So that gives me 3 times 1, which is 3. 3 times negative square root of 6 is negative 3 square root of 6. It's over. Multiplying the conjugates is supposed to be pretty easy. Thinking about FOIL, product of the first, 1 times 1 is 1. Because it's a sum and difference, you don't worry about outers and inners. Product of the last, positive times a negative gives me a negative. What is the square root of 6 times the square root of 6? It's 6. So one more line, and then I'm going to do these other problems on just the notebook paper that's in here. I'm going to have 3 minus 3 square root of 6 all over negative 5. Is that okay for number 30? All right. Starting with number 31, I have an equation, and we have not done an equation that is a radical equation. So let's see. Square root of 3x minus 2 minus 4 equals 0. Okay, radical equations. The only thing that's really different about radical equations is that you have to check your answers. Do you remember back when we were doing chapter 7? We had equations with fractions and we had to worry about domain issues? Well, it may not truly be a domain issue with this, but when you square, we're going to do some squaring. When you do the process that it takes to solve these, sometimes you introduce answers that won't check in the original problem. So, radical equations need to be checked. Okay, so we're going to want to check these. Solving a radical equation. The first thing you do is isolate the radical. So if there's something added or subtracted on the side with the radical, you need to get rid of it. So I'm going to add 4 to both sides. Now I have the square root of 3x minus 2 is equal to 4. In solving equations, don't you always do the inverse of what's going on? If it has x plus 2, you subtract 2. If it says 5x, you divide by 5. You're always doing the inverse. The inverse of square root is squaring. So I'm going to take the square root of 3x minus 2 equals 4, and I'm going to square the left side. Whoops. And square the right side. What happens when you square a square root? The radicand just kind of pops out. So I'm going to end up with 3x minus 2. No sign changes because that was all under the radical. It comes out exactly as it was, equals, when you square 4, you get 16. At this point, You might have a quadratic equation, you might have a linear equation. This one is linear. I'm just going to add 2 to both sides. That gives me 3x is equal to 18. Divide by 3, x is 6. Now I'm going to need to check that. And when you check it, you want to check it in the equation sometime before the squaring took place. So I could check it right up here. Okay? Is that on the screen? No. All right. The check. I'm going to have the square root of 3 times 6 minus 2, all under that radical, minus 4 is equal to 0. Do as little or as much work as you have to. In fact, you might be able to check it mentally. 3 times 6 is 18, minus 2 is 16. Square root of 16 minus 4 is equal to 0. The square root of 16 is 4, and 4 minus 4 is 0, and that checks. When it doesn't check, it's usually off because of a sign. It might have something like 4 minus 4 equals 8. Something where, oh, if there was just a sign different, it would have checked. That's the kind of issue you run into. Because what happens when you isolate the radical and you square both sides? Say this number was negative 4. And by the way, can a square root equal a negative number? No. But when you square both sides, everything becomes positive. And so no longer do you have that negative number in there. So sometimes a sign change happens when you square both sides, and that causes a false answer. That's why we check. This one does not have a false answer. The answer to this equation is 6. Anybody have a question on that? Okay, right here, the original equation was 3 times x minus 2. I got the answer, x is 6. Okay? So, going back up, that was number 31. X was 6. And you notice that you do have an option, there is no solution. That would be in case the answer you got didn't check. All right, let's look at number 32. Hopefully, well, I won't remember, but... Whoops. Trying to get myself a little bit more room. And it's not working very well. There we go. All right, 32. It is the square root of 27 minus x is equal to x plus 3. All right, in order to solve a radical equation, I need the radical isolated. Is it isolated? Yes. So the next thing I want to do is take the square root of 27 minus x and x plus 3, and I'm going to square both sides. On the left side, what happens when I square a square root? It just pops out as 27 minus x, equal sign. Now, the right-hand side you're going to want to be very careful with. I don't know how good you are, how comfortable you feel about squaring a binomial. I'll remind you. Square the first for x squared. Multiply those for 3x, but then double that because it represents both the inner and the outer product for 6x. Square the last one for plus 9. If you don't feel good about that, feel free to take x plus 3 times x plus 3 off to the side and do it by FOIL, where you'll have x squared is the first, 3x is the outer, 3x is the inner, and 9 is the last. Combine like terms, and you would get the x squared plus 6x plus 9. Okay, so it's your choice. You want to square it, Using the shortcut, great. If you don't feel good about that, use FOIL. What kind of equation have I got now? I have an x squared in it. I have a quadratic equation. That takes us back to the end of chapter 6, okay, where we solved quadratic equations. It's all beginning to run together for me. All right, I want it set equal to 0. So I'm going to subtract 27 from both sides. And I hope you feel okay about this. In the same step, I'm going to add x to both sides. So I'm doing two things, but what does it accomplish? 27's gone, the x's are gone, I get a 0 on the left-hand side. I need one of the sides to be 0. I have x squared. 6x plus 1x is 7x. And what is 9 minus 27? Minus 18. So I have 0 is equal to. The only technique that we know right now for solving a quadratic equation is factoring. So this better be factorable. I know I'm going to have 1 plus and 1 minus, an x and an x. I need factors of 18 that, because of the signs, have a difference of 7. 9 and 2, and I'll make the 9 be positive and the 2 be negative. The 0 factor property says that x plus 9 equals 0 or x minus 2 equals 0. So x is negative 9 or x is positive 2. I'm going to have two answers to check in just a minute. The first one I want to check is x equals negative 9. The original problem is the square root of 27 minus x equals x plus 3. Plugging in negative 9 for x. That's going to give me 27 minus a negative 9 is equal to negative 9 plus 3. Minus minus, that's going to turn into plus. The square root of 36 is equal to negative 6. What's the square root of 36? 6. Does 6 equal negative 6?
Negative 6 squared would be a positive 36.
Right. But that means that that's what happened. This answer of negative 9 would have checked in the squared equation. But it doesn't check in the original because this is just not a true statement. Okay? So since it didn't check, you need to get rid of that answer. But that's what I meant when I said if it doesn't check, it'll be because of a sign. All right, now we need to check x equals 2. I have the square root of 27 minus x is equal to x plus 3. I'm sorry. So that's going to be the square root of 27 minus 2 is equal to 2 plus 3. 27 minus 2, that's the square root of 25, is 5. And what is the square root of 25? 5. And 5 equals 5? That's good. This turned into a quadratic equation, but only one of the two answers I got in the quadratic equation checked. There's a possibility that they both check. There's a possibility that one checks like it did in this one, and there's a possibility that nothing checks and you get no solution. And I can't tell when I look at a problem what's going to happen. I have to physically go in there and do the problem. Is everybody okay with 32? 32 was a really good problem as far as being toward the end of this course because it makes you go back and draw on the quadratic equations that you had to factor. That will happen to you all the time in college algebra. You're just doing things and here comes a quadratic equation. And the expectation will be you know how to factor, you know how to solve it. Okay, so do me proud in there. All right, let's see what's next. Oh, we have a few more equations. So let's look at 33. I'm going to go ahead and do it right here. I have the square root of, and I'll pull this back down. I know you can't see it in class. 2x minus 3 is equal to 3. All right, to solve an equation with a radical in it, what's the format got to be? Radical isolated, is it? Yes. So I can go in, and I'm not going to rewrite it to do this. I'm just going to remember that I need to square the left side and square the right side. On the left side, the square of a square root, the radicand pops out, equals square the right side for 9. This is not quadratic. This is linear. So I will add 3 to both sides. And I have 2x is equal to 12. Divide by 2. And x is equal to 6. Is that okay? Let's check it. I start with the original equation. The square root of 2x minus 3 is supposed to equal 3. Plugging in a 6, that's the square root of 2 times 6 minus 3 is supposed to equal 3. 2 times 6 is 12. 12 minus 3 is 9. Is the square root of 9 equal to 3? Is 3 equal to 3? Yes. So that checks. Everything's good in that problem. Okay, I think we have one more equation, and then we're going to meet the imaginary numbers. Just what you were looking forward to. Whoops, I went the wrong way. All right, the square root of 5x plus 2 plus 2. The square root of 5x plus 2 plus 2 equals 0. Is this radical equation ready for me to square both sides? No. I need to go ahead and subtract 2, and I get the square root of 5x plus 2 is equal to negative 2. What's next? Square both sides. That's going to give me 5x plus 2 is equal to positive 4. It's linear. Subtract 2. I have 5x is equal to 2. Divide by 5. Don't cry. X is the fraction, 2/5. Okay, we need to check it. It won't be a hard check just because it's a fraction. I have the square root of 5x plus 2 plus a 2 equals 0. So that's the square root of 5 times 2/5 plus 2 plus a 2 on the outside equals 0. What happens right here? when you have 5, which is really a 5 over 1, times 2 over 5. The 5's cancel out, and you have the square root of 2 plus 2 equals 0. That's the square root of 4 plus 2 equals 0. 2 plus 2 equals 0. No. That's not true, which means that answer doesn't work. So what is your answer? There's no solution. Now, let me show you where earlier in this problem, now I can't always see no solutions. I really can't. Once in a while I can. This is one where we could. Look right here. Can y'all see? I don't know where my little big dot went, but we got a little speck. Right at the line where I squared both sides. Before I squared it, it said the square root of some number is equal to negative 2. Is a positive square root, no sign in front of it, is just a plain old square root going to equal a negative? No. But see, when you squared both sides, the negative went away. And so that's when it's dangerous. You have to do it, but you might introduce an answer that won't check. That's what happened in this problem. Any questions on that? No, that's exactly right. If you have the square root of, say, 4, it can only equal a positive 2. Now, the negative square root of 4, that could be read as the opposite of the square root of 4. Now, that could be negative 2. But a positive square root can't be anything but a positive number. Okay, so we did 33 and we did 34. Those are above this. All right, now it's time for imaginary numbers, starting with number 35. And I want to do a little discussion about imaginary numbers. All right, let me ask you a question. The square root of 25 is equal to what? It's equal to 5. And if I said, well, why? Because 5 squared is 25. Everybody agree with that? Now, what if I ask you, what is the square root of negative 1? Well, can it be 1? Is 1 squared negative 1? Okay. Could it be negative 1? Is negative 1 squared negative 1? Can I square any number and get a negative 1? Okay. Mathematicians, now what I'm about to tell you is not exactly historically the way it may have happened. So I'm using a little teacher license here to make this up. Mathematicians recognize this as a problem. And anytime mathematicians realized they didn't have a number to represent something, they made up the numbers. When they had 2 minus 5, and they said, I don't have an answer for that, they made up the negative numbers. When they had 6 divided by 7, and they didn't have an answer for that, they made up fractions. So mathematicians made up sets of numbers anytime they needed them. Well, they needed a number. There weren't any more digits to use. So what they did was they used a letter. They used the letter I. And I try to always make it a lowercase I, and when I write it, I try to give it a little tail so it looks a little italicized. The square root of negative 1 is defined to be I. And we'll go on and say, because I squared equals negative 1. Now you're going to want to remember this fact, or these facts. Whoops. That was supposed to be yellow. No, the I squared always just equals -1, and the square root of -1 equals I, and I think your question has to do with, what about the other negative numbers? What do I do about those? So we're about to find out. If I say, what's the square root of -1, your answer is I. But if I said, what's the square root of -4, it is 2I. What you do is break it into the square root of 4 times the square root of -1. You don't ever have to show this. But what is the square root of 4? 2. And what is the square root of -1? I. So the square root of -4 is 2I. It's as if you took the square root, but because it was negative, you added an I to the answer. If I said, what's the square root of -20? Do you agree that I has to be in the answer? Okay, now 20. So I might start out, it's the square root of 20 times the square root of -1. Can you simplify the square root of 20? Can you break it into two radicals, one of them being a perfect square? This is from yesterday. What times what gives you 20? One of them is a square. Right, 4 times 5. And that's still times the square root of -1. So I'm going to have what? What's the square root of 4? 2. And I don't know what the square root of 5 is. And what's the square root of -1? I. Well, it doesn't go under the radical. And you have to be careful. I don't have a problem with you writing the answer just like this. But traditionally in math, especially when they were doing typesetting for books, this is before computers and so on, they were real concerned that the I might be sitting too close to this and somebody would think it's under the radical with the 5, and it's not. So what they always do when they have an I and a radical is they put it in front of the radical. Now, I honestly don't know how Math Lab would react to this question, and I don't have the answers printed. You could show me an example and just look at the form of the answer and see if they think that's a big enough deal that they put it in there. I think either one should be correct. I don't have a problem at all with either one. You'll have to kind of check with Math Lab. Okay, so got the idea of the imaginary numbers? Little bit further. This is everything I've shown you was a pure imaginary number. All the numbers that we ever study, all of them, fit into a big set called the complex numbers. Okay, complex numbers are all the numbers. Now, inside here, there are two subsets, as well as numbers that don't fit into either of the subsets. One of the subsets is the real numbers, the ones that we are most comfortable with. The other subset is the set I've just introduced you to. These are the pure imaginaries. There are numbers outside of this. And what the other numbers, the other complex numbers have, is that they have a real part and imaginary part. And it looks kind of weird. They have, perhaps, 6 plus 3i, 7 minus 4i, 2 minus I, -8 plus 4/3 I. Those are examples of complex numbers. Complex numbers always are in the form a plus bi. They always have a real part, I call it a. It can be plus or minus a number times I, which is called the imaginary part. Now, you haven't seen any of those, but you will before we leave today. You'll see them in action. Now, real numbers. Real numbers are sitting inside this complex big blob. So real numbers are kinds of complex numbers. If I said the number 5 is a real number, well, how does that fit into this form that all complex numbers are supposed to have? What's the imaginary part? It's 0. When we deal with real numbers, the imaginary piece is always 0. So if I had the real number 17, as a complex number, it is 17 plus 0i. A real number is a complex number whose imaginary piece is 0. Imaginary numbers. 6i, that's an imaginary number. What's its real piece? It is 0. It is 0 plus 6i. If I had the imaginary number negative 1/2 I, what's its real part? 0. So every number in existence is a complex number, and they can all be written in the form a plus bi. There are numbers within this group whose imaginary parts are 0. We call them real. There are numbers within this group whose real parts are 0. We call them pure imaginary. And then there are the numbers all out here that have both pieces. Okay? Now, I can remember in my graduate work taking a course, and I was doing calculus processes, but the things I was working on had complex components to them. So, I was about at the same point that sometimes you feel I was thinking, oh my gosh, this is weird. Who uses this? So when I needed the answer to that question, I went to a physicist. I happened to have a physics professor who was also a friend. And I said, when in the world am I going to use these equations that have complex components and I've got to do the calculus? And he said, oh, that's what defines circuits and blah, blah, blah. And I went, okay, yeah, I'll just keep studying. What turned out, I didn't really understand his answer. I didn't have the physics background to do that. I was reassured somebody uses it. It just would never be me. So you may feel that way about some of these, but then again, as we finish chapter 11 and as you go to college algebra, you're going to see these complex numbers pop up in different places, and they usually tell you something important. All right, let's go back to our chapter 10 work, and not to number 1, though. All right, we just finished solving equations, and I am at number 35. Number 35 says, express in terms of I, and it has the square root of negative 63, and it says type an exact answer using radicals as necessary. All right, I need to simplify this. Okay, 9 times 7. So I'm going to need 3 radicals this time. You're welcome to do it in your head if you want. Perfect square is 9. Non-perfect square is 7, and I also have a negative 1 tacked on there. So what is the square root of 9? 3 times the square root of 7, and the square root of negative 1 is I. It could be that the best form for writing this would be 3 times I times the square root of 7. I don't have a problem if you have the I at the end. But once again, it was just a printing issue is the reason that they put the I in front of the radical as opposed to behind the radical. Let's look at 36. It says to write the negative square root of 250. Okay, 25 times 10. Now, is there a factor of -1 under the radical? No. So this is negative square root of 25 times the square root of 10, which is -5 times the square root of 10. Now the instructions say, simplify your answer, type as an exact answer using radicals as needed. Express complex numbers in terms of I. Now, I can't, unfortunately, unless I already had, well, I could go into Math Lab and look at this. I need to check and see whether they expect me to put plus 0i on that. So I'm going to pause and we're going to go look. Okay, so hopefully I'll get the answer to the question whether you have to put the 0i on there or not. It is a real answer, and so perhaps they do want that, but I'm not 100% sure. All right, starting with number 37, we're actually going to do some things with our complex numbers. Number 37 says to add and simplify. And then it says write your answer in the form a plus bi. So we are going to have complex form answers. So number 37 is 3 plus 7i plus 8 minus 6i. And this should feel a lot like working with polynomials. It's not a polynomial, but it should feel like it. You're going to do the same thing. You're going to combine like terms. This is addition. 3 is a real part. 8 is a real part. If you're supposed to add those real parts together, what will you get? 11. 7i is an imaginary part. Negative 6i is an imaginary part. If you combine those like terms, what will you get? You will get plus an implied 1i. That is your complex answer. If you add two complex numbers together, you will get a complex number. And notice that it's in the form a plus bi. What is the value of b in this statement? 1. Okay. So watch for that in the instructions when it says type in your answer in the form a plus bi. It didn't say that in the previous question, but it did tell me to write the answer as a complex number. So I was a little uncertain whether it wanted the plus 0i or not. All right, number 38. It is subtract and simplify. So I have 7 plus 2i minus parentheses negative 8 minus I. What do we do when we have subtraction? What do you have to do to the second set of parentheses, everything over here? You're going to have to change the signs. It's as if you're distributing a negative. Now, I'm going to change it, and you might want to watch. I'm going to change it in red. I'm going to say this is the same as add, opposite, opposite. So you're adding the opposite of the second one. Now it's an addition problem. Add the real parts. 7 plus 8 is 15. Add the imaginary parts. 2i plus an implied 1i is 3i. And there we go. Is everybody okay with that? Same thing you did with polynomials. Number 39 begins some multiplication. You're going to do the forms of multiplication that you already know, but don't forget one little fact. This will be very helpful to remember this. What is I squared equal to? -1. Keep that in mind for always, I squared is negative 1. All right, I have 8i times 9 minus 5i. What kind of multiplication am I going to use in this problem? Distributive property. 8i times 9 is 72i, and 8i times negative 5i is negative 40i squared. What is I squared? It's negative 1. So here's what I'm going to do. This is negative 40 times I squared. I'm going to get rid of the I squared. In my mind, I'm replacing it with multiplication by a negative 1, and that will always change the sign of the term that it belonged to. I squared is equal to negative 1, and negative 1 times negative 40 is positive 40. So this is, and it wants my answer in a plus bi form. What's the real part of this answer? 40 plus 72i. Every time I have an I squared term, I'm going to get rid of the I squared and change the sign of the term that it belonged on. All right, let's take a look at number 40. Number 40 has 2 plus 8i times 2 minus 8i. Even though this does not show radicals, everybody knows that I is really the square root of negative 1, so it kind of has the rules of radicals. What would you call these two? They're conjugates. These are conjugates. So I'm going to make a little note about that. Something very nice happens when you multiply conjugates, just like it did with real conjugates. The product of the first, I'm using FOIL. 2 times 2 is 4. The outer product is negative 16i. The inner product is positive 16i. Those are opposites. That'll always happen. The product of the last, what's 8i times negative 8i? Negative 64i squared. Ding, ding, ding. There's an I squared. What do? Get rid of it, but what happens to the negative 64? It becomes a plus 64. This is now 68. And if they want the answer in a plus bi form, it's going to be 68, what? Plus 0i. So it's a complex number, but it was real. That means that the imaginary part had to be 0. I personally would never require you to add that plus 0i, but MathLab might. So when you multiply conjugates with complex numbers, you always get something that's real. All right, another multiplication. I have negative 3 minus 2i squared. Do you want to use the shortcut, or do you want to write it out twice? Both? Yeah. Okay, let's start with the shortcut, and then if you don't like the shortcut, we'll write it out twice. The shortcut in squaring something that looks like a binomial is to square the first one. Negative 3 times negative 3 is 9. Then multiply the two terms. Let me scoot this up so there's not much else. Okay, what do I get when I multiply negative 3 times negative 2i? I get 6i. That represents the outer and the inner. So I need to double it. It's not going to be 6i, but 12i. Then I square the last. Negative 2i times negative 2i is positive 4i squared. If this were a polynomial, I would be done. But it's not. It's a complex number. And does everybody see I squared? And what does it do? Okay, all right, that goes away, and this becomes negative 4. That's a pitiful negative sign. It changes the sign of the term. So that is now 9 plus 12i minus 4. Final answer, 9 minus 4 is 5 plus 12i. What would that have looked like if I had multiplied it out using FOIL? I would have had negative 3 minus 2i times negative 3 minus 2i. Product of the first. Negative 3 times negative 3 is 9. The outer product is 6i. The inner product is 6i. The product of the last is plus 4i squared. I squared goes away, changes that to a negative. I have 9 plus 12i minus 4, or 5 plus 12i. If you prefer to write it out twice because you know you won't make a mistake that way, then by all means do it. Okay, adding complex numbers, add the reals, add the imaginaries. Subtracting, change your signs, then add the reals, add the imaginaries. Multiplication, you're either going to use distributive property or FOIL. Well, now it's time for something that looks like a fraction. It is division. And, okay, we've got a little bit of room here. All right. Problem number 42 has 8 divided by 1 plus 2i. Yes, you will. Because I really represents a radical, you do the same thing you did with radicals. You're going to multiply the top and the bottom by the conjugate of the denominator. So it's going to be times 1 minus 2i, 1 minus 2i. In the numerators, I'll use the distributive property. That's going to give me 8 minus 16i. In the denominators, I have product of the first, which is 1. Then I have outers and inners, which don't count. Product of the last, minus 4i squared. But what do you do with the I squared? Gone. Change. It is 8 minus 16i over 5. Now, I wouldn't mind you leaving that answer. Math Lab says, write your answer in the form a plus bi. And this isn't quite in the form a plus bi. What you're going to have to do is let that be a and let that be b. It's going to look like 8 over 5 minus 16 over 5 times I. And there will be an I in the tool palette, although I believe that if you just hit I on your keyboard, that'll work also, I think. So this is the form it wants, A plus or minus B times I. Okay, let's do one more of those. This is 43. I have 8 minus I over 6 minus 5i. If I would like this to be in the form a plus bi, I want only a real denominator if there could be one, what do I need to multiply by? The conjugate, which is 6 plus 5i. 6 plus 5i. Now, ready for a little bit of work. What am I going to have to use in the numerator to multiply? I have 8 minus I times 6 plus 5i. FOIL. Okay, so I'm going to use FOIL. Product of the first. 8 times 6 is 48. Outer product, 8 times 5i is 40i. Inner product, negative I times 6 is negative 6i. Product of the last, I have negative I. Yes, I'm just working on the numerator. I have negative I times 5i, which is negative 5i squared. And although I'm going to clean it up in just a minute, does everybody recognize that the I squared is going to go away and that's going to become plus? All right, and I'll finish taking care of that in a minute. I need to go ahead and multiply the bottom. Product of the first is 36. Outers and inners cancel. Product of the last is minus 25i squared. There's another I squared. Get rid of the I squared, change the sign of the term because I squared is equal to negative 1. All right, that gives me, in the numerator, do you see a 48 and a plus 5 are the reals? Okay, so that's going to be 53. Then I have 40i minus 6i, which is 34i. And that is over 61. And how will my math lab want the answer written? 53 over 61 plus 34 over 61i. Although it might not seem like a big deal, it is a big deal that if you add two complex numbers, the answer you get is complex. If you if you subtract 2, you get a complex. If you multiply, you get a complex. You divide, you still get a complex. If you do any arithmetic with complex numbers, you get a complex number. The answer is 53 over 61 plus 34 over 61 times I. All right, last topic. There are 3 questions. That say, what is I to a particular power? I to the 14th, I to the 37th, I to the 15th. So I want to have a little discussion about that. I want to talk about the powers of I. Now, this does not happen with real numbers. With real numbers, pick a real number, 2. If you raise 2 to the 2nd power, you get 4. 2 to the 3rd power, 8. 2 to the 19th power, big jumbo number. It doesn't work that way with I. I is very unusual in what happens to it when you raise it to powers. You have I to the first, everybody knows that's going to equal I. I squared. What is that equal to? Negative 1. Now, the next one, I to the 3rd. Okay, do y'all agree that I to the 3rd could be written as I squared times I? Because of the product rule, I would add the exponents. A 2 and an implied 1 would give me a 3. But this is -1. This is still I. So I cubed is equal to -I. Just bear with me. We're going to create a little group of numbers here. Whoops. I to the 4th. Let's see. I think I'd like to write it as I squared times I squared. Well, what's I squared? -1. And I squared is still -1. What's -1 times -1? It's 1. So far, I have 4 different values that powers of I can take on. It could be I, -1, -I, or 1. I to the 5th. Do you agree that that could be I to the 4th times I? Well, what's I to the 4th? We found out, we decided it was 1, so it's 1 times I, which is I. I'm not going to do this forever. I to the 6th. Isn't it I to the 4th times I squared? But I to the 4th is so nice because it's just 1, and I squared is -1, so that's equal to -1. Did I? No, it's just -1. Because I to the 4th is 1, and I squared is -1. I to the 7th. That's I to the 4th times I to the 3rd. I to the 4th is 1. I to the 3rd was -I. So that gives me -I. I to the 8th is I to the 4th times I to the 4th, which is 1 times 1 or 1. All right, I'm torturing you with this. The pattern. I to the 1st is I, then -1, -I, 1. If you keep going in patterns, it goes I, -1, -I, 1. And it continues that pattern forever. Just the 4 values. Now, what if I said, okay, how about what is I to the 22nd power? Now, here's something you can do. You can just count 4 over and over. Okay? So if I said, and I'm just going to sit here and tap, to get to 22, it's going to be, well, I don't know if I could tap this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Do what? Uh-huh. I'm sorry. Those of you in class couldn't see what I was doing. I was counting to 22, and there were 5 sets of 4 plus 2. Well, every time I hit a 4th one, that's I to the 4th, that's 1. So it's 1 times 1 times 1 times 1 times 1. Now what is I to the 2nd? What's the second number? -1. This is -1. It's the same as, those don't count, it's the same as I squared, because there were only 2. Okay, let's do another one. What is I to the 15th? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I don't worry about those because those were all equal to 1. So it is I to the 3rd, which is what? -I. Now, if I ask you, what is I to the 247th power? I do not want to go 1, 2, 3, 4, 5, 6. I don't want to do it. So, what you said about the groups of 4 was perfect. What I'm going to take is 247 and see how many groups of 4 are in it. Okay? All right, there are 61 groups. And he did it on his calculator, but I could have done the division. 61 times 4 is 244. And you know, there's only one number up here that matters to me. And it is the remainder. The groups of 4, that keeps on being I to the 4th, I to the 4th, I to the 4th, and those are all equal to 1. So, I to the 247th is the same as I to the 3rd, which is negative I. When you study this kind of pattern where a number, it just keeps cycling back over, it's called modular math. And you actually studied it when you were in elementary school, when you studied the clock. Because what does the clock do? 12 hours and then starts back over with 12 hours again, unless you live on a military base, and then it goes 24 hours and 24 hours. But, okay, it was supposed to be funny. I did grow up on this is pretty bad. I have to announce my jokes. I did grow up on a military base, and so we got used to, in some sense, military time. All right, but that is modular math. Sometimes it's called clock arithmetic. All right, your questions, and you will have 3 of these. If I can. Okay, number 44 says, what is I to the 14th power? You are welcome to either tick it off or do your division. If you have 14 divided by 4, that's going to go in 3 times, which is 12. The only thing you should care about is the remainder. So I to the 14th is the same as I to the 2nd, which is negative 1. So you should have written down that it is I, negative 1, negative I, 1. If you get a remainder of 0, then that means all there were groups of I to the 4ths, and that would equal 1. Okay, I to the 37th. What are we going to do? 37 divided by 4. It's going to go in there 9 times for 36 with a remainder of 1. Yes, I to the 37th is the same as I to the 1st, which is just I. And the last one on here is I to the 15th. So it's going to be 15, divided by 4. It's going to go in there 3 times, 12, remainder 3. This is I to the 3rd, which is negative I. The powers of I just cycle through those 4 numbers. Okay, we did equations with radicals where you have to check answers. We did calculations with complex numbers, and finally to powers of complex numbers. And that concludes everything we're going to talk about in Chapter 10.